Thank you. Yeah, it's great to be back. Thanks everyone for being here. So I guess I should start by explaining the abstract probably made it sound like, this is going to be me denouncing everyone in Oxford and saying everyone is wrong. And I guess, I wrote the abstract that way so everyone would be here to see what's going to happen. But it's not going to be quite like that. It's more that there is this thing that a lot of people in and associated with Oxford say that we'll get to, that, I just started thinking about why do people say that? Is it actually true? And I think there's a very flat-footed way of reading it, which I do think is just false. And then there is something which I think is, if I ask James or Ollie, why do you say this? What I would expect them to say, but we'll see about that. And I think that's not what I would like to say. But then there is something that I would like to say that will in the end render this thing that everyone in Oxford says true. So, we're all on the same team. So what is this thing that everyone says? Well, okay, so it's the Oxford consensus. So Ollie, for example, says, note that M1 and M2 are isomorphic structures, the possibilities they represent, therefore, because they're isomorphic, involve exactly the same pattern of qualitative features. Neil Juan, there's default in Oxford, part of the Oxford consensus says, in general, then, we will suppose that isomorphic models are qualitatively synonymous. The worlds they represent differ at most over which objects play which roles. Non-isomorphic models, however, represent qualitatively different worlds, or at least at first pass they do. I mean, I guess Neil's a little bit more hesitant here, but what is interesting is he's sort of giving both directions, right? He's saying isomorphic, qualitatively identical, non-isomorphic, qualitatively distinct. So we've got James Reed as well, who says something quite similar. When M1 and M2 are isomorphic structures, they represent the exact same pattern of qualitative features. And Thomas Monro-Nielsen, again, very different, very similar in spirit. The models in question are isomorphic. They represent worlds which differ at most, which regards to which particular objects are playing which qualitative roles, i.e. they represent worlds that are at most haecceitistically distinct. And I should admit that I've also been known to say something along those lines. Right? By definition, isomorphic models have the same structure. That is, isomorphisms preserve the relations between the elements of the domain. Therefore, again, isomorphic models represent qualitatively identical possibilities. So I guess, there is good reason for calling this something like a consensus. And so I've just gone ahead and called this principle Quine. Qualitative identity by mathematical equivalence, which just says exactly the thing. Pairs of models present qualitatively identical worlds if and only if they're isomorphic to each other. So I mean, I think from the quotes it's clear that it's the right to left direction that's sort of the most interesting one, right? If these models are isomorphic, then they're going to represent qualitatively identical worlds, so worlds that are at most haecceitistically distinct. But it does seem that people generally believe it goes both ways. So hence the if and only if. And I should note, Quine is weaker than some of these other principles presented by Fletcher and sort of refined by Pooley and Reed, right? Because they say that, sort of roughly speaking, isomorphic models represent numerically identical worlds, right? They just represent the same possible world. So I'm not talking about that. I feel that's a slightly different debate because I'm talking about this weaker condition. Good, so let me explain a bit more about what I mean by isomorphism and by qualitatively identical, because they're obviously the sort of tricky, relevant terms here. So isomorphism, I mean, I'm just going to do the easy thing and talk about these sort of set theoretic models. So we're not talking about difficult things like manifolds and so on. We've just got domain and some properties and relations and maybe functions defined over that domain. But, I guess there are ways of extending this to talk about more physically realistic models. But just when we've got a pair of models with possibly different domains and with index predicates defined over those domains, then they're isomorphic, if and only if there exists a bijection between the domains, such that this condition holds, such that the sort of extensions are preserved given this isomorphism. I think this should be relatively uncontroversial. So yeah, sorry.
Would there be a dash on the P, capital T in the last line, the very last line, similar being P dash?
Yes, thank you. Yes, there should be a dash on the capital P in the last line. Yes. Good. So qualitativeness, I think, is the more problematic notion, right? So roughly, we'd say something like non-qualitative properties are those which, in some intuitive way, make direct reference to a particular individual, right? So typical example of a non-qualitative property would be something like being identical to Caspar Jacobs or being the uncle of Caspar Jacobs, right? Because that refers to the individual Caspar Jacobs. And vice versa, qualitative properties are not about any particular individual. They're about nothing. I mean, you could read that two ways. Obviously, they're about something in the world, right? But no sort of thing, no particular individual. But that's only really a sketch. And it's very unclear if there is something more to say, right? So certain glosses that one finds sort of refer to linguistic signifiers, so they'll say things like, non-qualitative properties are represented by predicates that somehow involve proper names or constants. But those sort of things are all quite tricky, right? So one possibility, for example, is that actually individuals have qualitative essences, in which case being identical to Caspar Jacobs would actually be something like a hidden definite description of some sort of complete qualitative profile of me, in which case it might after all be qualitative. So we can sort of come up with more complicated scenarios in which the linguistic signifiers don't track the qualitative non-qualitative distinction. So I'm not going to offer a more precise definition. I'm just going to leave this here as a reminder. We have this intuitive distinction, but it's difficult to really precisify it. And I think in the literature, there are not many proposals that seem satisfactory. And there are some people who've just argued that it's the primitive distinction. Good, so let's return to Quine. The first question we can ask about it, is it true? But I mean, that's a very broad question. And I think a more interesting question is, if it is true, is it true of all, any pair of isomorphic models whatsoever, or only of a certain interesting subset of models, right? So I think the sort of very flat-footed way of reading Quine, and I don't want to imply that anyone, who was quoted means it this way, but I felt, at least for me, reading these quotes, it could sometimes feel as if that was all there is to it, which we should say any pair of isomorphic models whatsoever, right? However we interpret them, they're always going to represent qualitatively identical possibilities and vice versa. So I think that's wrong, and I'll offer some counterexamples later. But it seems that a more defensible version of Quine would say it's true of, for example, only the models we use to represent physical systems, and only under certain representational conventions, right? That would be a restricted version of Quine. That seems more reasonable. And I think then really the question is, right, if it is true of some relevant class of models, what makes Quine true? And that's where I might have more of a disagreement with the Oxford consensus, because I can imagine that many people would say it's due to certain representational conventions we use that sort of enforce Quine. And I have some reasons not to like that approach, but I want to offer a slightly different approach, which has more to do with this idea of, what is it to be qualitative? So we'll get to that. So first, let me just talk about this sort of unrestricted version of Quine, which says it's true of any pair of isomorphic models. Right? So in this view, it'd be due to the nature of isomorphism that isomorphic models could only represent qualitatively identical possibilities. Oops. I think there are counterexamples in both directions, so let's just provide them. So non-isomorphic models that represent qualitatively identical worlds, this is the sort of the uninteresting direction that doesn't play as much of a role in philosophy of physics. And I think the counterexample isn't going to be too controversial either, but just consider these models. We've got them here. They're non-isomorphic. Why? Because, in the first model, sort of R and M have the same extension and G and B have the same extension, but in the second model, R and D have the same extension and G and N have the same extension. And those are different, right? So there is going to be no bijection between D and itself. That's going to preserve the extensions of all these four predicates.
So the bottom line should have capital C, not D.
Yes, thank you. Yeah, sorry. Good. So those are the models. Now consider these dictionaries. I'll go back to the models later, but we're saying R means X is red, GX means X is green, NX means X is identical to Isaac Newton, and DX means X is identical to Du Châtelet. Okay, so the D could be a C there as well. But it's Du Châtelet, so that's why. Good. So now if we go back using that dictionary, in the first model, that's basically saying, right, the thing that's in the extension of being red is the same thing that's in the extension of being Newton, i.e. Newton is red, right? And the thing that's in the extension of being green is in the same as the extension of being Du Châtelet. So Du Châtelet is green. Whereas in the second model, in this dictionary, that's going to represent Newton being green and Du Châtelet being red, right? And so those are qualitatively distinct possibilities because color is a qualitative property, and being identical to Newton or Du Châtelet is a non-qualitative property. So we've got this sort of different qualitative distribution, right? And I should sort of clarify, obviously there's more to the world than just these primitive haecceitistic properties and colors. Newton wore a wig and Du Châtelet did. So we're sort of imagining that, I'm using these names to make it more vivid, but we could sort of imagine fundamental particles that just have this sort of color property, and we've called them, N and C. Good. So that's a counterexample in the one direction. So the example turns on the possibility that, we've got these haecceitistic predicates. And indeed, some philosophers believe that one sort of must represent haecceities this way. So I think Weatherall and Fletcher have views like this, right? Because for them, isomorphic models, right, they believe in this sort of stronger principle. Rumi, isomorphic models are always going to represent the same possibility. So if one then would want to present haecceitistically distinct possibilities, one would have to introduce additional structure, which is going to break the isomorphism, and that structure then represents haecceitistic properties. But I mean, we don't need to believe that, right? We could just say that it's possible to represent haecceities this way. It's also possible to let the elements of the domain themselves represent haecceities. But I think this at least sort of shows that, this sort of view might be acceptable. And it's also just reminiscent of Quine's observation that one can always replace names with predicates, right? So we could always sort of put the haecceitistic importance of names into our theory's predicates, and only, let the names sort of signify nothing, or the elements of the domain. Good. So more interesting, perhaps, is the other direction, whether isomorphic models represent qualitatively distinct worlds or whether they can. So here is one counterexample. Right, suppose we've got these very simple models. There's one predicate, and in both models, the predicates have the same extension. Right? They're identical, so clearly they're isomorphic. But now I suppose that F is going to be Rosalind Franklin, Px is going to mean X is red, but P prime X is going to mean X is green. Then these models are going to represent a world in which Rosalind Franklin is red, respectively green. So again, because color is a qualitative property, those worlds are going to be qualitatively distinct, even though the models are in fact identical and therefore isomorphic. So this might sound unfair because the interpretation of predicates should remain constant, right? P and P prime, they're sort of meant to be the same predicates, that are meant to have the same interpretation. Right? So Brian Roberts puts this well. He says, any two single element sets are isomorphic to each other, but one can use these sets to represent a black raven or to represent a white shoe. but one cannot use them both to represent the same thing at once on pain of paradoxes of multiple denotation. Right, so really what we want is, can isomorphic models represent qualitatively distinct worlds under one and the same interpretation? But I think they can do that as well. So consider these models. So now we've got a domain containing two objects, R and G, and we've got a single predicate B. And in the first model, R is in the extension of B, and in the second model, G is in the extension of B. And again, this means that the models are isomorphic, because if we map R onto G and vice versa, right, then that's going to realize an isomorphism. However, consider the following dictionary. R is going to represent a red object, G is going to represent a green object, and B is going to represent the property of being bright. Under that dictionary, the first model represents a bright red object, whereas the second model represents a bright green object. Now again, color is qualitative, so these worlds, insofar as they're sort of worlds, but imagine that they represent a world which contains just this one object. There's one bright object that's either a red one or a green one. They're going to be qualitatively distinct, even though the models are isomorphic. So I think that's a counterexample to the unrestricted version of Quine in the other direction. So the example turns on the possibility that now elements of the domain represent qualitative features, right? We sort of build in redness or greenness, not as a predicate, but as into sort of the membership of the domain itself. And that might seem unusual, but I don't think it's forbidden in any way. I mean, I think that I've just presented you with a pair of models and a way of interpreting those models in a way that you can make sense of. You can sort of see why the model represents the world I claim it represents. But in fact, it might not even be unusual. So in physics, I think we very often represent properties that we think of as qualitative as the elements of some structured domain, right? So think of a vector space, elements of which represent field values. We might think of field values as being qualitative features of the world, right? They're sort of properties instantiated by space-time points. But in a vector space, the field value would be represented by the element of the domain. So different elements of the domain then represent different qualitative properties for a space-time point to instantiate, right? And you could do a similar thing with things like a mass value space or points in a fiber bundle. They're all sort of elements of the domain that seems to represent qualitative properties. So I'll come back to this because maybe actually this is sort of the wrong way to think about these cases in physics. But I think, the fact that one might be inclined to think about the way physics represents properties this way, at least shows that it's not sort of absurd to use elements of a domain to represent qualitative properties. So I think that these examples show that Quine is not true of any model, any pair of isomorphic models interpreted in any way whatsoever. And I also don't think that's a surprise, right? Because Quine links this formal property isomorphism with this sort of metaphysically weighty distinction between qualitative and non-qualitative properties. And I've just mentioned at the beginning that explicating quality in terms of linguistic features isn't going to work. But here it seems we're doing something similar. We're trying to match the idea of being qualitative onto the formal feature of being invariant under isomorphisms. But again, it's sort of, if you're skeptical of formal definitions of quality in the linguistic case, then I think we should likewise be skeptical of doing it in a sort of model theoretic way. But as I said, it might be possible to restrict Quine so that it becomes true. And I think that is possible. And I think then the question is, what is the thing that makes it true? So let's move on. Here is a suggestion. Quine is true for models of physical theories, right? Maybe we need to restrict that further. Maybe it's something like mature physical theories or, mathematicized physical theories. But I just mean the kind of mathematical theories that philosophers of physics look at. So classical electromagnetism, general relativity, I suppose quantum theories, although I haven't really put them through, right? But those sort of theories, classical mechanics in a differential geometry framework. And the suggestion also has a suggestion for why Quine is true for those models, namely because we're working with a particular representational convention in which Quine will be true, right? And that's why it's restricted to those models of those theories, because in any other context, we might use different representational conventions. But the claim is, within the interpretation of those physical theories, we like to use a certain representational convention, and that representational convention makes Quine true for the models of those theories. Right, so I think Bellot, for example, is quite explicit about this. He says, we assume that only appropriately qualitative relations are represented in our structures. So objects related by symmetries will be qualitatively indistinguishable. So Bellot talks about symmetries rather than isomorphisms, but it's at least often the case that symmetries are isomorphisms. So we can sort of see how there is a connection here between Quine and, what Bellot rightly calls an assumption, or what we could call a representational convention, where we just stipulate this is how we're going to use those models. And I think that quote from Neil Dewar that I showed at the start also had this sort of flavor, right? He said something like, we will assume that isomorphic models are qualitatively synonymous. But I think there's a problem with this suggestion, which is that if Quine's truth depends on a representational convention, then Quine can't play the role in symmetry arguments that it's often taken to play, right? So, I mean, the reason people like myself and the other people quoted appeal to Quine is that it plays a certain role in a particular argument, which is as follows, right? So we've got this problem, which is that the symmetry-related models of theories seem to represent distinct but empirically equivalent possibilities. So this is sort of a problem of underdetermination, right? And there are different ways of putting it. So one thing one could say is the quantities that vary under those symmetries are undetectable. So if we assume that symmetry-related models represent distinct states of affairs, then we seem to have a bunch of quantities whose values we can't detect even in principle, right? And that might seem unparsimonious, or it might seem to violate Occam's razor. So this is often seen as a problem, right? And this is a fairly standard response to that problem. The first observation would be that in an appropriately formulated theory, whatever that means, symmetry-related models are isomorphic, right? So this might either just be an observation of a particular theory, or it might be a normative claim that one should reformulate theories in such a way that their symmetry-related models become isomorphic. Now we invoke Quine and we say that if models are isomorphic, then they represent qualitatively identical possibilities. Right? So this is why this direction of Quine is sort of the most interesting, plays a role in this argument. Then we could invoke another principle, anti-haecceitism, which says, I mean, this is my way of putting it, if possibilities are qualitatively identical, then they are numerically identical, right? So it says there don't exist any distinct yet qualitatively identical possibilities. Now, from this, it's going to follow that symmetry-related models represent one and the same possibility, right, known as Leibniz equivalence, and that means that underdetermination is averted, right? So in this sort of standard solution to something like the whole argument, or shifts and boosts in classical mechanics or gauge transformations in electromagnetism, Quine plays an essential role. But if Quine just follows from a more or less arbitrary convention, then the conclusion of this argument would only be something like there exists a convention such that symmetry-related models represent one and the same possibility. And then one could reasonably ask, why adopt that convention rather than another, right? It's sort of, then we still have those two, even given anti-haecceitism, it seems that we still have two possibilities. Either we could adopt the convention on which Quine comes out as true, and we can interpret symmetry-related models as physically equivalent, or we could adopt another convention on which Quine is true, and they still seem to represent distinct possibilities, right? So there is another convention possible in which the conclusion doesn't follow. So what's required then is some reason to prefer Bellot's convention over any other convention, right? And I think people have sort of tried to give arguments for this, so let me just discuss two. and explain why I'm not quite happy with them. So the first one is sort of an appeal to naturalness. So in their paper, Puli and Reed say this: it bears stressing how natural and apparently appropriate it is the particular use of isomorphic models to represent at most haecceitistically distinct possibilities. A substantivalist who believes that possible spacetimes can differ merely haecceitistically is after a way to represent the structure of such a spacetime, and at the same time talk about two possibilities that exemplify the very same structure, but differ over which individuals possess which particular properties. How better to do this than to use isomorphic models of the appropriate structural type that differ merely over which of the base elements of their sets are assigned to structural properties common to both models, right? So I don't think the passage was intended in this way, but one could here read an argument in favor of Quine, namely it says the representational convention on which Quine is true for the models of physics we're interested in is, a particularly natural one. But this raises some questions. So one is, why assume that natural conventions are better, right? Why should we use the most natural convention? Another question is, intuition about what is natural may vary, right? So I can imagine that someone like Weatherall would say, actually, it's very unnatural to use isomorphic models in this way to represent those haecceitistically distinct possibilities. And instead they should always represent the same possibility. But I think actually my sort of biggest problem with this style of approach is that ultimately, right, this argument I just presented wants to establish a non-natural interpretation of symmetry-related models, namely as representing the same state of affairs, right? So it sort of feels a bit self-undermining to say the most natural way of interpreting those models is as haecceitistically distinct, but qualitatively alike. Use that assumption to defend Quine, but then end up with an argument that says we should represent our models in a way that's not natural by this standard. Good, so there's probably more to be said here, but let me move on to another thing that people sometimes have implied about this particular representational convention, which is that it just follows from a literal way of understanding the theory's models. So Oliver Puli says the theoretical treatment of spacetime read literally strongly supports haecceitism, and Thomas Müller-Nielsen says something similar. Read literally, non-isomorphic gauge-related models of this particular version of electromagnetism assign qualitatively distinct arrangements of the vector field over spacetime. Now, I have to admit, I find it hard to make sense of these remarks because to me, it just seems that a mathematical formalism doesn't have a literal interpretation, right? Normally, when we think about literal as opposed to metaphorical interpretations, the language already has a literal interpretation, right? If I think about something like biting the bullet, literally that means, someone is biting a bullet. But the only reason we can say that has a literal interpretation is because those words, bite and bullet, we can sort of go into the dictionary and find their literal interpretation. When we're looking at uninterpreted models, I don't think there is a literal interpretation like that we can appeal to, right? We're in the process of interpreting those models. There isn't one that sort of comes embedded. So that's one issue. And then the other issue is the same one that we encountered before. Ultimately, the aim here is to use Quine to establish a non-literal interpretation of isomorphic models on which they represent not just qualitatively identical worlds, but numerically identical ones. So again, it seems a bit fishy to use an appeal to literalness to ultimately defend non-literalness. Okay, so this was everything sort of negative I had to say about why people might be wrong. But now I want to say that, there might be a different way of understanding Quine that hopefully we could all agree on. So let's try that. So far, we've mostly focused on isomorphisms, right? And sort of the unrestricted, flat-footed way of understanding Quine says it's just due to the nature of isomorphic models that they can only represent qualitatively identical possibilities. And I've given counterexamples to that. And then we sort of said, okay, maybe there's a way of setting up a representational convention, which is such that isomorphic models represent qualitatively identical possibilities. But, I've already said it's sort of difficult to get something interesting about quality out of something, you know, formal about isomorphism. So I think a different approach would be to start by looking at what we mean by quality, or what we could mean by quality, because as I've said, right, it's sort of still a very undefined, slippery notion that we've got a rough understanding of, but no real idea of, you know, how we would define it. So there are two versions of the proposal I have in mind. The first proposal, call it primitivism, so that qualitativeness is something out there, right? It's just a primitive fact about properties or relations that they're qualitative or non-qualitative. But we might have some good reason or another to believe that within, you know, the particular area of physics that we're interested in, qualitative properties are represented as being invariant under isomorphism, right? So think about this a bit like you might think about laws, right? Say we believe that laws are just primitive out there, right? But we seem to have good reason to believe that the laws are represented by, say, the axioms and theorems of our best sort of deductive system of the world, right? I mean, there is more to be said about why we would then believe that. So one thing might be just good old inductive reasons. We might think so far, for all the cases where we've had a clear idea of when one property is qualitative or not, it seems that the qualitative ones are always represented as invariant under isomorphism, and then we might sort of generalize from there and say, well, maybe that's, you know, going to be true for all of physics. Another stronger view would be empiricism, and it's the qualitative properties just are the properties that are represented in physical theories as being invariant under isomorphisms. So this is analogous to empiricism about the laws, right? It would say the laws just are the axioms and theorems of our best deductive system of the world, right? And again, this could be motivated by a combination of sort of inductive reasons. We'd say, well, it seems that so far the things we thought were laws always also seem to be the things that were the axioms and theories of our best deductive system. But then it'd be sort of supplemented by intuitions about, you know, what it should mean to be a law, or what it should mean to be qualitative. So, I mean, maybe these are helpful things to say to contrast these. So one thing is we could think in terms of something like real and nominal definitions. So we could think on primitivism, Quine gives us a nominal definition of quality. Under empiricism, it would be something like a real definition. I don't know if that analogy will sort of break down at some point or not. And another way to see it is to say that under primitivism, we get the extension of quality rights given Quine, whereas under empiricism, we would get the intension of quality rights. I mean, I hope that's a little bit helpful. I haven't really thought those analogies through. So it's hard to think about this suggestion, right, sort of why we would believe those things. So I do think there is sort of an argument to motivate either primitivism or empiricism. I think the argument is neutral between those two views. But the argument might be sort of controversial in itself, so we'll see. So here's the argument. The first premise would say a property is qualitative if and only if it is dynamically efficacious, right? It sort of plays a dynamically relevant role within the theory. So why would we think this? Well, it's basically inspired by Mervel's interpretation of Ehrman's principles, SP1 and SP2. I should have put the citation up there. But basically, Mervel says, when we think about space-time structure, right, qualitative space-time structure, we think that there is an analytically true connection between that and between the dynamics. So he has a few sort of intuition pumps, right? One is something like, suppose we live in an Aristotelian universe. So in fact, everything is attracted to the center of the universe. That's part of the dynamics. Then according to Mervel, and I'm sympathetic to this, that can only be true if there is something sort of qualitatively different about the center of the universe, right? It's not just that everything is attracted to the center of the universe because it has the haecceitistic property of, you know, being that point C. Everything is attracted to the center of the universe because it has the qualitative property of being the center of the universe, right? It need not be a property that's sort of a monadic property that the center has. It might be something sort of more structurally complex related with the whole space-time structure, but it has to be qualitatively distinguished, right? And vice versa. If I just said, you know, this point over here has a very special qualitative property, then we just think that was nonsense unless I could give you some dynamical reason for believing that, right? So the only thing I'm trying to do here is I'm saying, well, Mervel's a very clever guy and he said this, and I'll just declare my allegiance to what he said there. And also I want to extend it to the non-spatiotemporal cases, right? So even if we're talking about, say, mass, for example, right? And if we want to know what is qualitative about mass, then it has to be whatever it is about mass that also plays a role in the dynamics. If I said there is a special mass, but I couldn't sort of prove that dynamically, then I'd just be talking nonsense. So second premise says a property is dynamically efficacious if and only if it's represented by features of theoretical models that are invariant under isomorphism. This, I think, is motivated by recent work by people like Descopter, David Wallace, and at a more formal level, David Baker, have sort of given similar arguments for thinking that the structure of our theories that's variant under isomorphisms is, you know, dynamical danglers, or they're biphenomenal quantities. The way David Wallace puts it is he sort of says that the dynamics you know, sort of can be completely separated into the variant and the invariant bits in such a way that the invariant bits have their own self-sustaining dynamics that the variant bits of the theory have no influence on, right? So this premise, I think, could be contingent, right? This need not be a necessary truth about all of physics. I'm happy to leave open the possibility that in some future physical theory, features that are variant under isomorphisms might be dynamically relevant, depending on, you know, the way one writes down the dynamics. If that's true, then Quine would likewise just be contingent. So that would rule out, I think, the stronger empiricist principle, and we'd have to revert to this sort of primitivism and say, given premise one plus this contingent feature about our theories, Quine might follow, right? So then from this, it's going to follow that a property is qualitative if and only if it's represented by features of theoretical models that are invariant under isomorphisms, which is basically identical to Quine. So that's a rough and ready argument for Quine that I'm sure could be improved and relies on some controversial premises, but it's one way to motivate it. Okay, so now let me turn to a case study just to see what we can do with this sort of new defense of Quine, right? So what I want to look at very briefly is color charge in sort of a fiber bundle formalism. So what we have here is we have a color field represented by a section of an associated bundle to the SU3 principal fiber bundle, or maybe that's just a bunch of gibberish. If you haven't looked at all this stuff about fiber bundles, but I think the sort of essential idea is we've got the space-time manifold, and then we've got this other manifold, which is the associated bundle, and we've got a section which maps any point on the associated, or maps, you know, provides a map from the space-time into the associated bundle. So we've got a map between manifolds, right? But it seems natural to say that the color field values, which would be the points on this fiber manifold, are qualitative, right? If we would assign different field values to the same space-time point, we might think that's a qualitative difference, because the things that exist in our theory are the space-time points, right? And they instantiate various properties. And if we just change the properties they instantiate and we leave all the space-time points the same, then it seems that should just be a qualitative change. But here's the problem. Gauge transformations are fiber bundle automorphisms. So from Quine, it's going to follow that gauge-related models, right, models which have rejigged this distribution of field values over the space-time manifold, are actually going to be qualitatively identical. So you might think this is a problem for my defense of Quine, right? And indeed, this sort of sounds similar to the counter-argument to unrestricted Quine I gave earlier. But I think in this particular case, it's actually a virtue. I think it's correct to think of color field values as being non-qualitative, right? So there are various reasons to think this. So one goes back to this argument: the color charges themselves are dynamically inefficacious insofar as a gauge transformation doesn't affect the dynamics, right? Models related by a gauge transformation are what you might call co-dynamical. It's the relations between the charges that are important, right? So those will be things like parallel transport relations across the bundle. There'll be sort of group relations between points on the bundle. Those are dynamically relevant, but the color charges themselves are not, right? So one way of seeing that is, suppose we've got a world in which every space-time point is assigned the same color, green. I know these are not real colors, right? But you know, the color we call green. And suppose in another possible world, we've assigned every space-time point the color red, then those models are going, and those worlds indeed are going to be dynamically exactly the same. There's nothing that distinguishes them. So it seems that, you know, just being red or being green is dynamically irrelevant, right? It's by the relative color relations that matter for the dynamics. So that's one reason to think this is the correct verdict. Another reason is just to stress this analogy between the space-time manifold and the fiber bundle manifold, right? And there have been philosophers like Arnsenius and Joe Wolf who have developed views which you could call something like quantity substantivalism, on which we really should think of those value spaces, including fiber bundles, as being substantive, right? So if we're using a particle ontology rather than a field ontology, then the idea is just in the exact same way that a particle occupies the location in space-time, where that location is a separate sort of thing, it also occupies a location on this fiber bundle manifold, which will also be a thing, right? So it won't be a qualitative property, it's an object. And I think it also matches this idea of sophistication, which Neil Dewar has developed and which I've tried to defend a little bit, right? Because sophistication wants to say that isomorphic models are physically equivalent. It wants to do that. The way Neil sets it up is, in the case of, say, space-time symmetries, we declare anti-haecceitism. So we say that there's only qualitativeness to the world and nothing non-qualitative. But then in the case of, say, fiber bundle symmetries, anti-haecceitism wouldn't work, right? Because now those models of, say, electromagnetism related by gauge symmetries on the sort of naive reading are qualitatively distinct, right? So then Neil Dewar introduces another principle called anti-qualitatism, which basically says even certain qualitatively distinct worlds are actually numerically identical, right? But on my view, this would actually be covered by anti-haecceitism, because now the points on the fiber bundle also represent particulars rather than qualitative properties. So it sort of simplifies this view, and therefore you might think supports it, right? So the point here is this way of thinking about Quine as a guide of what counts as qualitative, or giving us some hints about what is qualitative using the framework of physics, meshes well with various views that are out there in the literature. So we might sort of think that by itself, it might not be convincing, but putting all those views together, we might think we've now got a nice coherent package of views about the kind of possibilities that models represent, about isomorphisms, about quality, and sort of as a group, that's a nice view to adopt. So let me just briefly summarize everything that I've said, and then we can go on to questions. So I've said that the most straightforward interpretation of Quine, in which it's unrestricted and applies to any pair of isomorphic models whatsoever, is false. And again, I should stress that I don't think there is any explicit textual evidence to think that anyone I've quoted holds this unrestricted view. But it's one way of reading those quotes. Defenses of Quine based on representational conventions fail as well for the reasons I've given. But we could think of Quine as a definition or a guide to quality, either implicit or explicit. And I've said that's sort of the best way to think about it, and that together with sophistication and with quantity substantivalism, it gives us a really nice coherent way of thinking about what isomorphic models represent in physics. Thank you.